This video is to introduce you to the summation of torque activity, and the purpose of this lab is to introduce you to the concept of torque and how we can sum torques just like we do forces. Torque is essentially, we've introduced the idea of angular motion, where we have angular velocity and change in angle and angular acceleration, and we saw that those values corresponded to their linear counterparts. So your angular acceleration is related to your linear acceleration. Well, we have an angular counterpart to force, and that is torque, and it is defined as the force times the length of the lever arm. Now the force has to be at a right angle, and we're not going to get complicated in this class, so all the forces we deal with will be at a right angle to the length. So if I have a wrench or I have a crowbar and I'm trying to twist something, the twisting power, the twisting force I get is defined as how hard I push times the lever arm. Those of you who have ever tried to undo a bolt, if it won't come undone, you either have to push harder, increase the force, or you can lengthen your lever arm, get something to make this longer, and the same amount of force will loosen the bolt or break it, one or the other. Now, just like if our acceleration in the linear realm is 0, our net force is 0, then if our angular acceleration is 0, then our net torque is 0. In this lab, the acceleration is 0 and we're not going to be moving. But just like in the linear world, you could be having a constant linear velocity and have a net force. You could have a constant, in fact, when you have a constant angular velocity, then that means you have a 0 net torque. So let's look at an example of how net torque sums up to 0. We have two directions that things twist in. They twist in clockwise or counterclockwise, which we'll see in a minute. So in this case, I have what we call a fulcrum point right here in the middle, and to the left I have a 6-meter lever arm, and to the right I have 3 meters, and the left force is 2 newtons and the right force is 4 newtons. So I'm going to have a left torque. I'm going to have this pulling down is going to make it go counterclockwise. This pulling down wants to make it go clockwise. So my left force is 2 and my left lever arm is 6. My right force is 4 and my right lever arm is 3. Now I'm going to figure out what the torque is. I'm going to have a left torque and a right torque, and my left torque, my alpha is 0, is what I'm getting ready to say here. I have no acceleration, so I know my torques are going to sum up to be 0. That means my torque on the left, which is trying to go counterclockwise, is going to equal my torque on the right, which tries to go clockwise. And we can see that's true. My torque on the left is the force times the lever arm. So 2 times 6 is 12, and 3 times 4 is 12. We also know something else. We know that we're not accelerating linearly either. So the net forces in all directions, in the linear sense, the net forces have to be 0. So that means my force pushing down on this board have to be equal to my force pushing up. Well, my force pushing down is going to be 6, so that means I'm going to have a force pushing up right here at the fulcrum is also going to be 6. So I can add that force in. So I can draw a force in there of 6 newtons going up. So my torques are balanced and my linear forces are balanced. Now it turns out my torques have to be balanced everywhere. So we originally worked the problem where I was saying my torque was balanced around the fulcrum. But if my torques were not balanced here, then this whole stick would be spinning this way or this way. It would be accelerating. So we're going to find out that I can pick any spot I want on the board, and that's what we're going to do in the lab, and show that the torques are balanced, and it will always work. So now I have a torque right here that I'll call my torque pivot, okay, because that's where the board is. That's what we're going to call that in the lab, because that's the actual physical pivot point. So I have a force of 6 up, and I have a length of 6. So my torque around this point is 6 times 6, and that would be going counterclockwise because this fulcrum pushing up is trying to spin it this way. Now I'm going to do the torque due to the 4 newtons. Now I have this entire length, which is 9. I have the 6 and the 3, so I have a length of 9 times 4. That is also 36, but that's trying to spin it clockwise. So we now see that I can, and what we're going to do in the lab, we're going to do it for 3 different places with actual measurements and show that I can pick here, here, or here. And my torques are always going to be, if I'm not accelerating, my net torques will always be 0, so my counterclockwise and my clockwise will come out to be the same value.